start off having a little bit of a review on our orders of reactions and what we call our integrated rate laws, right? So we introduced last time, or last couple of times, we introduced the rate law, and we said how each chemical reaction will have a given rate law that's specific for that chemical reaction. And the rate law tells us the rate of the reaction, how fast the reaction proceeds, with respect to the concentration of the reactants, right? And that's why the equation for the rate law looks like this. The rate of the reaction is equal to, there is some constant because the units for rate are molar per second, right? So there's a rate constant to help the units work out. So the rate of the reaction is equal to the rate constant times concentrations of reactants. All right. So if that's if A and B are the reactants in some given reaction, now I'll put a 2 there, and I'll draw the product so it doesn't feel weird, but we want to make sure we remember that in the rate law itself, we only include the reactant concentrations because those are the ones that influence the rate of the reaction. All right, and these reactant concentrations may influence the rate on what we call a zero order, first order, or second order. Now, actually, when we say zero order, that means that reaction rate is independent, concentration independent. So it doesn't depend on that concentration of that. So, for example, if x equals 0 for this scenario, it means it doesn't matter how much A you put in. It won't speed up how fast the reaction occurs. Now, there's a variety of reasons in reality why that might be the case, and it's represented by a 0 there, or indicating that this is a 0 order with respect to A. This reaction is 0 order with respect to A. All right, so B might have a 2. I mean, just for a scenario example here, we want to kind of remind ourselves that the coefficients or the order of the reactants on the rate is not indicated by the stoichiometry. Okay, so you can't use the stoichiometry to predict those. There's only one way that you can identify the order of the reactions. Jace, do you happen to remember how we can tell the order of the reactions?
No, I forgot.
How about you, Sarah? Any ideas? How can we determine the order that the reactants have in the reaction?
I'm not sure.
All right. The answer was experimentally. Or in other words, you need to have data like this where you perform certain experiments in which you keep everything constant. For example, here in the difference between the first and the second experiment, keep everything constant except for one thing. We've only changed the concentration of one of the reactants, and see how the change in concentration influences the rate of the reaction, right? So the only way that you can determine the order of the reaction with respect to those concentrations is experimentally. Okay. And I don't know if you remember, but we would, for example, write down a skeleton rate law to start off with, look at 2 experiments where we only change the concentration of a single reactant, A and B, or first and second experiment here, for example. And we would see, right, that as the concentration of A doubled, the rate, what? More than just doubled, huh? It quadrupled. And you could put that into your calculator and verify that. But then that would mean that whatever the concentration here of this is, X, if the rate is going to go up to 4, then when we would double this X, it must have been second order with respect to that concentration. All right? If you don't remember how to do that, that's definitely going to be kinds of questions that will be asked. So you'll want to be able to go back and watch those videos and review that. Okay? Okay, so here was another example where we looked at rate, identifying the rate law and the rate dependence on those concentrations. And then we got to a point where we began to integrate the rate law. Integrate the rate law. Now, the reason why you might want to integrate a rate law is because the integrated rate law will allow you to know the concentration of a given reactant after a certain amount of time has passed, right? So I have a chemical reaction. I have a rate law that I've determined experimentally for this reaction, right? Concentration of A maybe squared, right? So I've determined all that stuff. Now what I'd like to know is, based on my rate law, if I start at time 0, right? T equals 0 means the beginning of an experiment, with a given concentration of A, how will my concentration of A be? What will it be after an hour or after X amount of time? How much A will I have left? And integrated rate laws allow us to do that, okay? So we introduced the zero order integrated rate law first last time. And the zero order integrated rate law looked like this. We were told that we're not going to have to memorize these integrated rate laws, but we do want to be able to look at them with enough understanding that we can see that they make sense to us, okay? Or at least to a degree they make sense to us. The zero order rate law here, you can see that if you take the concentration of A, and that can have, should have a T on it right there, the A with a little T there. The concentration of A at time T, let's actually put that T in there really quick. So it's a little t, meaning that concentration at this time, let's see, where's I don't have it on here, so I got to right click here. Sorry about this. I'm going to change the format here, or the font. There we go, subscript, right? Because that subscript T there, what that means is that the concentration at time T, whatever time you're interested in, equals the initial concentration. That's what concentration at time 0 equals, it means, minus the rate law, or sorry, the rate constant times time, however much time you allow it to be introduced for the reaction to occur, right? Okay, so we then also solved problems like this where we were given a chemical reaction, given a, well, we weren't necessarily given this reaction or this integrated rate law, but we were told it was zero order. So once we see that it's zero order, we would be able to choose this from a list, right, of 3, 0, first or second order reactants. And then given an initial concentration and a the rate constant in this case and the time, we could solve for the concentration at time t, right? We also did this one here where we were given the time, no, we were given the initial and the final concentration and the rate law, or rate constant, and we solved for time. Okay, and we also remembered that every rate laws, K, has the possibility of having different units, right? So let's take this rate law, for example. Rate equals K, A squared, we decided for the rate law for this chemical reaction. And we need to have enough ability and comfort with these rate laws to know what the units are for our rate constants. Okay, Sarah, do you think you could identify what the units would be for this K in this rate law?
I think I could. So rate is molar per second.
That's right.
And then
Mm-hmm.
Do you need to square them all at all?
Yes,
So
because of that. Yeah.
Okay, so it's m squared. So it would have to be 1 over molar times second.
Very good. I feel like we've been here like twice before. Don't you feel it, Sarah?
Yeah,
You could even give us the joke, couldn't you?
I could.
But you won't. Don't worry about it. But that's right. This is the pattern that we go to identify the units on K. Very good. Did you want to give the joke, Sarah? I didn't want to cut you off.
Okay. Well, how would we have to move the molars?
Yeah. How would we get rid of the molars? Let's see. Camille, do you have any ideas?
You go to the dentist.
That's right. Very good. Fabulous. At least you guys are learning one thing. Very good. All right. Yeah.
I have a quick question.
Yeah.
For the K, is that molars too? I can't tell if that was a capital or a lowercase.
This is big M here. And per second. And the way we knew that is we just knew that this had to be molars per second. And this is molar squared. So we need to get rid of 1 M here to end up molar per second, just like this side. So that's how we can identify what the K is. Just sitting down and looking at what units are on the right and the left, knowing it has to be molar per second. So, which of the following is the correct set of units for the rate constant for a zero-order reaction? And this is true for any zero-order reaction. Let's see. Camille, what do you think? Which ones are the correct units for K for a zero-order reaction? It is A. Very good. Okay, so because in a rate law where it's zero order, rate will equal K times whatever units reactants you have, but they're all to the 0. So these parts drop out, and rate molar per second will always equal the K value, so the units on K have to be molar per second. All right, we're doing a lot of good review here. Now, I don't think we did this problem last time. All right. So what it gives us is the starting quantity, and it gives us an amount of time, and it gives us a K, and it doesn't give us the starting quantity. It gives us the remaining quantity. 2.5 molar remain after the reaction. So we're going to identify what the starting quantity was, and we're going to break up into little groups and see if we can do this. Okay? So I'm going to create a couple of breakout rooms, and we'll see how we do. All right? Go for it. All right. Let's wait for Jace for a second. You there, Jace? You there, Jace?
Yeah, something's up with my mic, so I have to leave it and
Oh,
join it.
that's fine. So why don't you tell us, what'd you do? How'd you solve this one?
We used the equation
AT minus A0 equals KT, is that what you said?
No, I said AT equals A0 minus KT.
All right. So I'll put an equal sign in there because they're the same thing. So what'd you put in for AT?
We did 2.5 molar.
Let's see. Is AT, what is the starting quantity? Okay, so we're solving for that one. 2.5 equals,
Minus 2.3 times negative 10 times 10 to the negative 5 molars over seconds times 5 hours is the time, but we converted that to seconds and we got 18,000.
okay. So, it kind of wasn't very tricky what equation to use, because this is what we're talking about right now, our zero order reaction. We're reviewing it really quick. However, there is a integrated rate law for a first order reaction, an integrated rate law for a second order reaction. Did you guys know for sure that this was a zero order reaction, Jace, or did you not think about that?
Yeah, I was fairly certain it was the zero order because, like, I saw it. I mean, I might have wrote it down the wrong place, but I thought it was a zero order one.
Was there any reason we could know for sure?
Oh, well, for zero order, you always, no, for the rate, I don't know, it was M over S.
Yeah, that's right. That's right.
Okay.
The units on the rate constant allow us to know if it's first order, second order, or zero order, first order, or second order. Okay, and then then we know which formula to use. Okay, so did this work out to be 2.9 then? Excellent. All right, very good. So now would be the time to ask any questions if you had any questions on that one. So we'll move on to first order reactions. First order reactions, right? And the integrated rate law for a first order reaction looks like this. The natural log of the initial concentration, 0, A0, right, over the concentration at time t equals KT. And we said that first order reactions, let's see, that previous problem here, does it have to be in seconds? Is that what you're asking about, Camille? Yes, it does, because the K was provided in seconds, right? So we were going to have to take that 5 and convert it to 5 hours and convert that to seconds. Good point, right? The time, whatever time you put in to your equation, you have to make sure you have the same units on both sides. All right, so we made this plot. Wait a second, where's the plot? There it is. We have this plot that shows us how the concentration of our reactant disappears versus time. All right, concentration of a reactant, here this is just a radioactive isotope, disappears over time when it's a first order process. Okay? And first order processes have a fixed half-life. That means the amount of time it takes to remove half of its material is the same amount of time that it'll take to remove half at any given point, right? So going from 100%, let's say, down to 50%, if that takes one half-life, then going from 50 down to 25% will take the same amount of time, a second half-life. That's only true in these first order reactions. And that's one of the reasons why the natural log is used here, because the natural log means the log of Euler's number, and Euler's number has this relationship of natural decay or exponential decay. Okay, so that's our equation, right? And we'll want to be able to recognize it as the first order rate law and then answer questions like this. Okay? Let's see. We also said that because first order reactions have a fixed half-life, T, if you put in the half-life value in for this equation here, right, then your concentration, your initial concentration, if it equals A naught, will relate to your final concentration by just 1/2, right? So your final concentration will be half of your initial concentration at a half-life. And so this over this will always equal 2. And so we have this relationship where we can say the natural log of 2 equals the rate constant times the half-life. All right? And so that's another tool that we have available to us. Now, if you're only provided this first order integrated rate law, it's easy to get to this other second reaction, which is, again, a relationship between a number, natural log of 2 is just a number, and the rate law and the half-life, the rate law and the half-life. Okay, so last class we answered this question where we were told the half-life for this material, and we wanted to know what percentage remained after 24 hours, and we were, so with this initial information, we took this equation here, which was the natural log of 2 equaling k times half-life, k times the half-life. All right, and then we divided the natural log of 2 by k and set that equal to the half-life. All right, so then we can just plug in our numbers. Half-life 2.295 hours. Natural log of 2 over k, right? And we could solve for k there. We did the math, and we got this value. All right, and then we could find out what percentage would remain after 24 hours by using the same relationship, natural log of the initial concentration over the concentration at time t. This time we have our k, right, 0.302, and we know that the amount of time that we're going to allow it to pass is 24. This is in hours, but our rate constant is in hours as well, right? So we don't have to convert this to seconds. So I don't know if this is what Camille was talking about in terms of needing to be seconds. I should have said it doesn't need to be seconds, minutes, whatever, just as long as it's the same as each other.
Make it easier to put it in seconds?
Not in this case, because in this case we have already identified our rate constant in per hour, right? So it's easier at this point to keep them in hours, right? So we reminded ourselves last time that the natural log of a fraction like this is the same as the natural log of the top minus the top there, minus the natural log of the bottom, and we can set that equal to 0.302 times 24. All right, and we have, what other things do we have in here? Well, if we said that our initial concentration was 100%, that would give us just one variable to solve for. So I'll make this 100, and then we're going to be solving for this, and that'll be some value, x. So we go natural log of 100 minus natural log of x equals, let's simplify this right half of the equation, 0.302 times 24. What happened? $7.248. Okay, and then we made a mistake I made a mistake in the calculations last time because I took the natural log of 100. Let's do that first. Natural log of 100, 4.605. Right, then I could take 7.248 and subtract our 4.605, move it over to that side, 2.643. So last time I was here, I said the natural log of x was equal to this, but I forgot to bring down that minus sign there. So it's the negative natural log of x that equals 2.643. Okay, now we want to make sure everybody knows how to solve this sort of problem in their calculator, right? when I have negative natural log of x equal to negative 2.643. I guess it's easier to move the negative sign over on that side, divide both sides by negative 1, right? So now I need natural log of x equals negative 2.643. On the calculator, I go second, and then I click on natural log there. And so it's going to raise e to this value, which is a negative 2.6428. And then, what did I do? Let's try that again. I'll just type it in. Negative 2. I think I put the minus sign there. 2.643. There we go. All right, so the answer is 0.0711. And that is percentage, right? Because we put this up to 100, so it already is in percent of the, that's how much is going to remain after 24 hours. Okay? Now, let's think about that a little bit more, less mathematic maybe, kind of with just a reasonable mind for a second, as a double check, right? As a double check. Not that we don't trust what we just did, but you want to have a second way to always kind of double check yourself. If we think about this initially being 100 units of whatever of this material, right? 100 grams, we could say. And we want to know how many grams we're going to have left over after 24 hours. Well, Sarah, here's a question for you. If I started off with 100 grams of this material and I let it react for 2.295 hours, how many grams would I have left?
So,
if I start off with 100 grams of my reactant, right, let's just call this A, and I let it react for 2.295 hours, how many grams am I going to have left over here?
you would have 50 grams left.
50 grams, because 2.295 hours is one half-life. Very good. If I let it go for a second half-life, so I'm going to type in there 2.295. If I let it go for a second half-life, another 2.295 hours, how many grams would I have left, Sarah?
25.
25 grams. All right. So that's after 4.59 hours, I'm going to have 25 grams left. Another half-life. How much am I going to have left, Sarah?
12.5.
12.5. So after 6.885 hours, I'm going to have 12.5 grams. Another.
I'm going to have to pull out the calculator.
You can be rough about it.
6.25.
6.25 after 9 hours. All right. How about the next half-life, which is, 9, 11.
3.125.
All right, 11.5 hours. I'm going to have about 3-point-something grams. All right, where should we be if we get to 24 hours? How many grams did we say we're going to have? Should be 0.07, right?
Right.
Okay, so let's keep going. After 13 hours, how much am I going to have?
1.5.
16 hours?
0.7.
Oh no. 18 hours?
0.39.
0.39. 20 hours?
0.19.
23 hours?
0.097.
All right. So in one more hour, it wouldn't be unreasonable to go down to 0.07, right? So there's a rough way to double check, right, to make sure you're in the right ballpark. Okay, very good. So all of that was kind of review to catch us up to where we were